Hello students, you're welcome to your favorite educational program, Teaching and Learning on Radio by Niger State Ministry of Education. It promises to be interesting and it comes up every weekday. This is to keep the school children abreast of their curriculum due to coronavirus pandemic that has kept them at home. At this moment, we have our facilitator in the studio who will be taking you on a very interesting subject. Happy viewing. I am Kabir Yusuf.
Listeners at home, we're back again with the subject physics. The topic of discussion today is equations of uniformly accelerated motion. That is a topic mainly for SS2, but the SS3 student can also benefit. Now, at the end of this lesson, listeners at home should be able to deduce or derive the three equations of motion from the concept of acceleration and average velocity. 2, should be able to explain the terms and symbols used in the equations of motion. Then the third one, you should be able to use the equations of uniformly accelerated motion to solve simple problems. Now, let's start with the first objective. That is to deduce or to derive the three equations of motion. Before doing that, we know acceleration is defined as the rate of change of velocity with time. Now, from the concept, for example, if you have two bodies or a car traveling from Mina to Bida, this car moves with velocity. There is possibility that this car starts from rest. That is the initial velocity, maybe 0, or the initial velocity may be infinite. Then this car traveled to Bida, from Mina to Bida. It covers distance. And there is what? Time. Time is involved. Just as we define motion as the change in position of an object with reference to time from the starting point. Now the starting point is Mina, and this vehicle moves down to Bida. You see, it covers distance. There is change in time, and there is change in velocity. Now the velocity is from initial to final. Now, based on this concept, we are going to derive this first equation of motion. We said that acceleration, which is represented with small letter a, is change in velocity all over change in time. Now, this change in velocity here is from final, that is the final point, to initial in this case. Now, when we have a change in velocity, that is delta v, is equals to the final velocity, which is v, minus initial velocity, which is u. They are all measured in meter per second. Then change in time also, we have the time it takes for this car to reach Bida, that is T2, that's the final time. Then the starting time, which is from Mina, that is T1. In this case, the T1 here becomes 0 because the car is starting from rest. So our T1 will be equals to what? 0. And therefore, the acceleration now will be the change in velocity, that is v minus u, all over what? T. Because we said T2 minus T1, since the time reference here, that is the initial time taken is 0. If you say T1 is 0, then everything here will become 0. So we're left with only one T. Now, from this now, we said we multiply through this equation by T. And if that is done, A multiplied by T will give us V minus U all over T multiplied by T. Listeners at home, if you cancel T and T, we are left with V minus U. And this one will be A multiplied by T will be AT. So acceleration multiplied by time equals to V minus U. Now we make V, which is the final velocity. We make V the subject of the formula. And here we have V equals to U plus at. And this gives us the first equation of motion. That's the final velocity equals to initial velocity plus acceleration of the body multiplied by the time taken. Now, another way of getting this equation is simply by a velocity time graph. We're going to look at this velocity time graph in this form. So we have what we call the velocity time graph. We call it VT graph. And this now goes by this, the vertical line showing the velocity in meter per second. And we start with 0. The horizontal is t in seconds. So if this is done, you see the graph will start not from the starting point, but at a point, this is the point where object is already in motion. So this is point we call point P. Then this is our initial velocity here, u. Then we have another point here, which is point Q. Then at this point Q, we have our final velocity where the vehicle has landed, that is to be that in this case. Then it forms a gradient or a slope. And this slope gives us what you call acceleration. And that is, this is change in velocity all over what? Change in time. So this graph will surely give us the first equation of motion by derivation, because if you look at it, this is change in velocity, and the slope here, which is the gradient, is acceleration. So A is equals to V minus U all over what? T. By the time you multiply through by T, you still get the same equation of motion. That is V equals to U plus AT. That's why I say you can use this graph to still derive the equation of motion. Then, in a situation whereby the initial velocity is 0, the graph will also change. And this will look like this. It will look like this. That is V in meter per second. Then this is our time in seconds. Then here, we say the object starts from rest. That is initial velocity. You can see it's still a straight line graph. If this is point P, and we have our point Q here, then definitely we have our gradient. Let's put the gradient down. We have the gradient up to this point, so we have pointer PQR. Then here, which is the acceleration due to gravity gradient, is still the what? The acceleration, which is change in velocity, and this is change in time. Here, since the initial velocity is 0, the equation will change. So here we say V equals to U plus AT, and we say U is 0. So V now will be equals to AT. So that's the difference between this and this. For here, the car starts at rest with initial velocity 0. Now here, the car starts from somewhere. It's already in motion. So the counting of velocity starts from here. So that is the difference between the two. Once the body starts at rest with the initial velocity 0, then the equation will change. And that will give you V equal, that's velocity, final velocity equals to acceleration multiplied by time. Now, we have seen the first equation of motion. Let's move next to derive the second equation of motion. Now, the second velocity, the second motion, or the second equation of motion, can be achieved when we know our average velocity and the displacement, that's the change in displacement. Now, average velocity, that is AV, will now give us the initial velocity minus the final velocity divided by what? 2, since we are talking of average. Now, what is the average velocity here? Is the change in displacement. That is, I'll put it change in x, that is displacement, all over change in time. And this will give us the initial velocity, which is u, plus final velocity, which is v, divided by what? 2. Now, if you look at the change in displacement, it's the same thing as giving you S2, that is the final displacement, minus the initial displacement. Then change in time also will give us T2 minus T1. Now here, both x1 will be equals to 0, and t1 will also be equals to what? 0. And if that is done, we'll be left with x all over t. Will be x all over t equals to what? U plus v divided by 2. Now we also multiply through by t. We multiply the equation by t. If that is done, we have x all over t multiplied by t equals to u plus v all over 2 multiplied by what? T. Now this t will cancel this t. Our x now will be equals to u plus v all over 2 multiplied through by t. This is what we call equation of an average velocity. Now we're going to use this concept based on what I've said. We use concept of acceleration and concept of average velocity to derive this equation of motion. So the next step, we'll now use this equation to refer back to the first equation of motion so as we derive the second equation of motion. Now I will take this from up. Let me still have to bring the formula up. S equals to u plus v all over 2 multiplied by t. Now, from equation 1, we know that our v equals to u plus at. So wherever we see v, we substitute this value, u plus at. So our x, which is the displacement now, is equals to u plus at. It's clear. Divide by 2, multiply by what? T. So we further go ahead. U plus u will be equals to 2u. Is that not? 2u plus at into t divided by what? 2. Now we have to multiply the numerator by t. This will give us 2ut plus at squared. Then divide by 2 each, because you can still break it. You are dividing by 2 each. Now this 2 will cancel this 2. And x now will be equals to ut plus a half at squared. Very clear. So this one is the second equation of motion. That it says x, that is displacement, equals to initial velocity multiplied by time, plus an average acceleration due to gravity multiplied by what? T squared. Now, after getting this, we'll now use this concept of element without motion of element without time to derive the third equation of motion. And we move ahead again. We'll now use this second equation of motion, that is x equals to ut plus a half at squared. Now, if this is achieved, we'll still refer back to the first equation of motion, that is v equals to u plus at. In this case, we're dealing with time. So we make t the subject of the formula. And how do we do it? We now say v minus u equals to what? At. And therefore, t will now be equals to v minus u all over a. So we make t the subject of formula based on this first equation of motion. Now, wherever you see t, you now substitute v minus u all over a in the second equation of motion. So let's take that again. S now is equals to u. Then we go to t, that is v minus u all over a, close the bracket, plus a half a, then t square. So we say v minus u all over a all square. We have substituted the value of t from the first equation into this equation, into the second equation. Now we move ahead. X now will be equals to u v minus u all over a, plus, if you look at this, we are squaring a square. This a will be square, since v minus u also is square. It will not be, when you square it, you have half a into v minus u square all over a square. So we still further ahead. X now is equals to u v minus u all over a, plus a half, or this time let's put the half on there as the numerator. This a, one of the a will cancel, so we still have no a here. So this will be plus v minus u all square divided by what? 2a. We're left with 2a. That is clear. Then we look at it, we say, okay, let us look for the LCM. So if this LCM is 2a, a against a will cancel. So we have 2u left into v minus u plus 2a cancel 2a. We still have this v minus u all square x. Now our x now will be equals to 2u now will move down here. So we say v minus u plus 2u into plus 2u plus v minus u. There's no square again. So all will be equals to 2a. Now I will proceed. I will still proceed. So this will give us our x now, that is displacement. You multiply through, it will be 2ax is equals to v minus u plus v plus u. If you break it very well mathematically, then we still have 2ax into v square by the time you expand minus u square. Making v the subject of the formula now, we have v square equals to u square plus 2as. So this is the third equation of motion. So we end up deriving the three equations of motion here. The first one is v, which is the final velocity, equals to u plus at. Then the second one, we say s, which is the displacement, equals to ut plus a half at square. And the third one, which is v square, equals to u square plus 2as. This is how we derive the three equations of motion based on the concept of acceleration and average velocity. Now, the next one, we say we are going to explain all the times. And in the course of my study, I have been explaining the times because of time factor. We said our x there represents the displacement. Our v there is the final velocity, measured in meter per second. Our u there is the initial velocity, also in meter per second. Our g there is the acceleration, which the unit is meter per second square. So those are the three equations of motion. Now, if we want to look at these three equations, that is motion under gravity, that is acceleration of free fall. We see all this will now turn to minus. This sign is turned to how? Because, for example, if you are lifting a ball up, or you throw a ball up, it reaches a particular height, and this ball now comes down.